Hello, and welcome to another one in our series of physics and astronomy contexts. Today, we're going to talk about auroral current. And you see here the list of all of the people involved in this project, which is a project funded by NASA in partnership with Temple University and the American Association of Physics Teachers. So I'm going to begin by talking a little bit about magnetic field, because magnetic fields are generated by currents, where the current is a net motion of electric charge relative to the observer. Now, it can also be a changing electric field, a field that's changing in time. We call that the displacement current, but the kind of current we're most familiar with is motion of charge, like motion of electrons in a wire. That would be a very typical kind of electric current that we would be familiar with. So the mathematical relationship for the magnetic field and the current is given by Ampere's law. And it was James Clerk Maxwell who added the displacement current to Ampere's law. And actually that addition was gave Maxwell the ability to show that electromagnetic waves existed and they travel with the speed of light. But that is for another time. Now, here on Earth in the lab, I can turn on a current, and then that current makes a magnetic field that's consistent with Ampere's law. And at every point in space, the magnetic field produced by the current at that point is perpendicular to the current and to the line from the current to the point. So this means that magnetic fields are really, intrinsically 3D, because if I have a current, then the magnetic field is always perpendicular to the current. That always poses difficulty in drawing currents in magnetic fields. And it also poses difficulty in students understanding just the spatial relationships, even if they can understand the Biot-Savart law that tells you what is the direction of the current and everything from a given, or a direction of the magnetic field from a given current. The spatial manipulation in your mind of all of these variables may actually be very difficult. So this is something that students have problems with, is getting all those spatial relationships right. So we can begin with the magnetic field of a line current, which is really the simplest current you can imagine. It's just a current flowing along a long straight wire. And to get the direction of the magnetic field, you would point your thumb from your right hand in the direction of the current, and your fingers are going to curl in the direction of the magnetic field. Now, magnetic field lines always close. That's because there's another one of these fundamental laws of electromagnetism, Gauss's law, that says that there are no isolated magnetic charges. There's always a plus with a minus, a north with the south. And that means that all magnetic field lines must be closed. And it's a fundamental fact of nature. So the magnetic field lines around a current carrying wire will form circles, as indicated in this diagram. So here's a question for you. There's a current that's flowing directly above you, the thick line, and you are directly below the current. And you measure a magnetic field coming out of the page. And this is a typical kind of symbol used to indicate coming out of the page. It's like the head of an arrow. And if you see a circle with an X in it, that's an arrow going into the page. But here we have the magnetic field coming out of the page. And you have a choice. The current could be flowing in the direction indicated by A, that is, the current is flowing from the left to the right, or it could be flowing in direction B, from the right to the left. So I'm going to give you just a little bit of time to think about this and then answer the question, write it down for yourself. If you're viewing this as a video, not that you can just pause. Go ahead and pause it while you write down your answer. So the correct answer is B. The current, if I put my thumb in the direction of the current, then my fingers curl so that the paper or the magnetic field below the current is coming out of the page. And so B is the correct direction of the current. Now, what about if we take a few steps in the direction of the magnetic field? So that would be stepping out from the page. And we've already established the current flows from the right to the left. But if I take a few steps out from underneath the current in the direction of the magnetic field, which in this diagram would be out of the page, does the magnetic field point upward or downward at that point? So think about it for a moment. Decide, write down your answer, actually. That's a good thing to do because it forces you to commit to an answer. And the result is that if you're looking at the current, I've redrawn here the current. So now we're looking along the wire as the current is coming out of the page, out towards us, which means that we would be standing right about here. We see that the magnetic field is going to form a loop like this. It's going to form a circle. And so that right below the wire, it's coming straight out of the page, it's drawn up above. And that means that just outside of just beyond the page, we would have the magnetic field pointing up. Now, the magnitude of the magnetic field is given by a simple formula for a long line current. And I is the total current that's flowing in the wire, and mu naught is just a constant of nature, 4 pi times 10 to the minus 7, permeability of free space. And R is the radial distance to the wire. Now, all of these units are in MKS units. So I is in amps, R is in meters, and B, the magnetic field, is going to be in Tesla. Now, Tesla is a really big magnetic field, really big. The magnetic field on the surface of the Earth is just a tiny fraction of a Tesla. It's actually about 31,000 nanotesla, and that's 10 to the minus 9. So, it's 3.1 times 10 to the minus 4 Tesla. That's the Earth's magnetic field. So a Tesla is a really, really big magnetic field. Now, when we speak about the aurora, the story of the aurora really begins with the sun and the sun's magnetic field. And here on the right-hand side, we see an image of the sun in X-rays from a NASA spacecraft. And on the left-hand side, we see a white light image of the sun. And you can sometimes see these sunspots, which are regions of a little bit less brightness in the dark region on the sun, because there's big, intense magnetic field that has pushed the plasma out of that region, lowering the density, lowering the amount of light being produced. And that's why it looks a little bit darker than the surrounding regions. And here on the right-hand side, we have solar activity. And you can see these magnetic field lines, and they are evolving and sometimes stretching and breaking, releasing stored energy that comes from the twisting and the boiling and the churning of the sun. But the sun's atmosphere is so hot. I mean, this is like million-degree kind of image because it is an X-ray, that the sun's gravity can't hold the sun's atmosphere down. It's so hot, and it expands out into space, becoming what we call the solar wind. And when the solar wind hits a magnetized body like the Earth, then we get a cavity in space called the magnetosphere. The solar wind presses on the Earth's magnetic field, the Earth's magnetic field pushes back, and you get something that looks like a comet in space, if you could see the magnetic field. And it looks like a comet for the same reason that a comet looks like a comet. The solar wind is flowing down the tail, stretching the Earth's magnetic field out into this long tail. And what this really means, though, is that there are electric currents that are flowing through space, because electric currents make magnetic field. If I want to change the magnetic field, that means there has to be an electric current there somewhere that is making that magnetic field look the way that it is. And some of these currents flow along the Earth's magnetic field in and out of the polar region. And if those, here's an artist's drawing of those currents. If those currents are strong enough, then the atmosphere lights up. And we call that the aurora. And the details of the aurora are, it is kind of complicated, because it's the current actually, as it flows, it exceeds a certain threshold value, setting up an instability that creates a voltage that pushes enough electrons to close the current. But then that voltage accelerates the electrons, and they hit the upper atmosphere and cause the atoms to glow. So it's the details of it are complicated, but fundamentally it's a big current that lights up the sky that makes the aurora. And that current is driven by the solar wind flowing past the Earth's magnetic field, and a little bit of that energy leaking into our magnetosphere to create the aurora and other phenomena. And here's what it looks like at Space Shuttle altitudes, 300 kilometers. And these really are big sheets of electric current. And the bottom of those sheets, the bottom of the light, if you will, it's about 100 kilometers. And at that point, a lot of the current now is flowing horizontally to close through the ionosphere, flowing from space into the ionosphere and back out. Other planets have aurora too. Here we see Saturn and Jupiter, they have aurora. And just like Saturn and Jupiter, our auroras in both hemispheres, north and south. Now, the scientific age really began actually with the study of magnetism. William Gilbert, who was the personal physician of Queen Elizabeth I, published what is widely considered to be the first major work of the scientific era, where he did all kinds of experiments with magnets, disproved all kinds of old ideas that had been floating around since the time of Aristotle. And he did it through experimentation. And so he really was doing science. And among other things, Gilbert showed that the Earth itself is a great magnet. He was able to show this through a series of experiments and models, and make a scientific argument that the Earth itself is a great magnet. And that explained why a compass needle pointed north, because up to that point, nobody had an idea of just how a compass worked. Why did this needle, which they knew was a magnet, they knew it was magnetized, but why did it point north? That's because the Earth itself is a great magnet. Now, given that you had navigation by compass, and the fact that the north magnetic pole is not in the same place as the geographic pole, people started making maps of the difference of true north from where the compass needle was pointing, something called the declination. And George Graham, who was a watchmaker and a fellow of the Royal Society, made observations of the declination near London. And here he published his paper, An Account of Observations Made of the Variations of the Horizontal Needle at London in the latter part of the year 1722, beginning of 1723, by Mr. George Graham, watchmaker, FRS, Fellow of the Royal Society. As a watchmaker, he could make very detailed instrumentation. And so he made these very precise compass needles. And so he could make very careful measurements of the of the magnetic field near London, and he saw that on occasion the needle would just jiggle and very irregularly. And he tried isolating it by putting it in a glass shell, still saw the same thing. It didn't matter whether it was stormy or clear, day or night, hot or cold. But he published his observations. And later, these irregular variations were noted to appear during auroral displays. So there was some kind of connection between magnetism and the aurora. And Gauss and von Humboldt, who went around the world setting up magnetic observatories, and others, they showed that these, what were soon to be called by von Humboldt, magnetic storms, were global. Something was disturbing the whole magnetic field of the Earth, and it was somehow seemingly related with aurora. And aurora had fascinated people for centuries. Many, many myths about the aurora. In the scientific age, people tried to explain the aurora scientifically, and there were ideas. One that was very popular is that it was sunlight reflected off of ice crystals, which in the upper atmosphere. Well, that's not correct. Franklin actually produced the first electrical theory of the aurora. He thought the light came from thunderstorms, and this is a drawing from his paper that he published on the subject. He imagined that the equator was hot, so the hot air would rise and then circulate to the pole, where it would cool and fall down and then circulate back. A fascinating idea. We now call these things Hadley cells, after somebody who did the work after Franklin. But he thought that this concentrated flow in the polar regions would produce enormous thunderstorms and huge amounts of lightning, and that would create the light for the aurora. Fascinating idea and very interesting model, just not correct, but still the first electrical theory of the aurora. Now, Christian Birkeland was a Norwegian who obviously was interested in the aurora because he lived in Norway, but he was also a brilliant physicist. He was a student of Henri Poincaré. He published the first general solution of Maxwell's equations in the late 19th century. And then he went back to Norway to study the aurora. He built magnetic observatories. He did theoretical analysis because he was an accomplished theorist. And he also did experiments. And here he is in his lab where he has a magnetized ball called a terrella. He called it a terrella, and he's firing electrons at it, what were then known as cathode rays. And occasionally he would get little rings of light around the polar regions that looked like aurora. And so he suggested that these were caused by beams of electrons coming from the sun. That was the link to the sun, because people knew the sun had something to do with it, but they couldn't figure out a mechanism. So Birkeland drew these kinds of pictures. These are actually from his book. And he concluded that the electric current came from space and closed through the upper atmosphere. See, Birkeland didn't even know about the ionosphere. That was discovered later, but he had already postulated that there must be a conducting layer in the upper atmosphere for these currents to flow, and that they were of limited extent. They would flow horizontally, roughly in a line, because he had these magnetic observatories, and he was using them to make measurements of the magnetic field and to infer the currents flowing overhead. But Birkeland's arguments, well, were disbelieved by a number of people for many reasons, and in particular Sidney Chapman. He was a brilliant scientist who was a young man when Birkeland was old, and Birkeland at the end of his career did have some issues, which Alex Dessler, who's a very well-known theorist in space plasma physics, Alex has argued that Birkeland actually was suffering from mercury poisoning. You saw that picture of him in his lab. And in his lab, he had open vats of mercury for his pumps. And people didn't understand back then the dangers of mercury and the neurological effects, so that Birkeland's later writings were not so great, and he also had some strange ideas. Like his idea for the currents in space were fundamentally sound based on the magnetic observations, but he insisted that there must be something wrong with Maxwell's equations, because the sun wasn't charging up, but it had to be producing these beams of electrons. Later, we understood that there was a plasma, equal amount of positive and negative charges coming from the sun. But so Birkeland's ideas had some problems, although they were fundamentally correct, but they didn't work well with Chapman's style. And so he dismissed many of Birkeland's ideas. The fellow here on the right, he looks about the same age as Chapman, but they were actually about 20 some years difference in age. It's just that the pictures are taken at different times. And Hannes Alfvén was a Swede, and he thought that Birkeland's ideas were fundamentally correct. And he would argue against the mainstream scientific consensus. And actually, finally, with the space age, we could go and see for ourselves. And we found that Birkeland was absolutely correct. There were these electric currents flowing through space, closing through the ionosphere. And Alfvén in 1970 won the Nobel Prize, and Chapman never won the Nobel Prize, although he did Nobel Prize winning work, but he never won it. So these electric currents that now we know are coming from space can have effects on our environment, something that we call space weather. There's many things that happen in the space environment. There are high energy particles that are coming from the sun, but certainly when the currents in the ionosphere are very large, there are many effects, because those currents can create turbulence, and that creates bubbles in the ionosphere, bubbles of plasma that interfere with radio communications. We'll lose communications with spacecraft. And very importantly, the currents that are flowing in the ionosphere, as we've discussed, create magnetic fields. But those currents are not steady. So those magnetic fields are changing in time. And that is inducing electric fields in nearby conductors. And the biggest conductors around are things like our pipelines and our power grids. And those ionospheric currents and the change in the currents and the currents in our technology that they induce can be a very significant space weather effect. And in fact, the first great magnetic storm that had an effect on human technology, it occurred in 1859, and it was a huge flare, actually, that was accompanied by coronal mass ejection. And people were already then trying to say, well, you know, there probably is a connection between what happened on the sun and this magnetic storm on Earth. But it was an enormous magnetic storm with enormous effects. There was aurora seen at places you normally would never see aurora, like New Orleans, Galveston, Texas, Havana, Cuba. Even off the coast of Nicaragua, there was a US Navy ship that reported seeing aurora. And the telegraph, which was, you know, a big conductor, right? Long strands of wire that could carry this electricity being generated in the ground by the induced currents from the auroral current flow. Telegraph was basically knocked out for a better part of a week. And that was the internet of the day, the telegraph. And it was just, you know, really, really severely impacted. There was so much electric current flowing in the ground that there are reports of telegraph operators just sticking the bare wires into the ground and using that to power their telegraph instead of the batteries. And all of this was collected by Elias Loomis, a professor at Yale University, and published in a series of papers in the American Journal of Science. So how bad could a big storm like the Carrington event be? Well, actually, pretty bad. There was a National Academies report in 2008 that back then said you could have losses of $1 to $2 trillion and a recovery time of years, because you could really hammer our power grid, blow out really big transformers that we don't make too many of them. They're difficult to move around. So the threat of a major event like this and the impact through auroral currents is very real. And in fact, we did have an event that might have been something on the scale of the Carrington event, but that coronal mass ejection actually missed Earth. It went off in a direction perpendicular to the Earth-Sun line and just missed the Earth. But these things can happen. There have been a number of spacecraft missions, NASA missions, to study the phenomenon, and one in particular is the THEMIS mission, which has got both a set of spacecraft. There were 5 spacecraft launched together in a configuration to study the energy flows in space that power the aurora, and then also a bunch of ground stations with imagers and magnetometers to study the aurora and to make the connection between the auroral energy and the energy being released in space. And so the THEMIS mission has made a lot of progress in understanding these energy flows that power the aurora. So to conclude, it really is electric current flowing from space that powers the aurora. And these currents flow horizontally through Earth's ionosphere. And we call those currents electrojets. And we can remotely detect electrojets by measuring the magnetic field they produce. And actually, as you'll see in our activity that we've designed, the easiest sort of zero order assumption is you assume the electrojet is like a line current at 100 kilometers in altitude, and then figure out how much, you can figure out how much current is in the electrojet by looking at the magnetic field that you measure on the ground. And of course, if these currents are very, very large, like during a big magnetic storm, they can have significant space weather effects. Thank you.